All right, ladies and gentlemen, welcome to the beginning of the Calculus 1 YouTube series. This is Resh Mahaber, again, coming to you from Wayne State University. It is the beautiful May 14th, 2018. I am happy to be teaching Calculus 1 this summer, and I wanted to go ahead and try to make it as easy as possible with as much supplemental material as possible, since Calc 1 is the real change of mathematics. And when I mean the real change, it's exactly what I just said, the change. Up until now, you guys have done math where it's fairly simple. You know, solve this thing, and you get an exact value or exact one or two values, discrete amount of values. Or input this thing into this function, and you get out one thing, because that's what a function does. But that is not what calculus talks about. So let's take a second and talk about what is calc. Okay, I know I have an example underneath there, but I didn't want to get too far ahead of myself. So what is calculus? Calculus literally just examines how fast, how fast something is changing. Okay, I know those are three weird things that I just said. So let's talk about how much something is changing. Okay, so if we talked money, let's say you get hired at a job. Okay. And at year 0, which is the year you got hired, you make $40,000. Okay? But then, you know, for whatever interesting things, you are very motivated or not motivated. At some point in time in your life, you end up making $90,000. So what we want to talk about is something that's very interesting, and I think it's important you understand the verbiage. Math is a language, so understanding the verbiage is very important. The net change. Net change is exactly what you think it is. What do I mean by exactly what you think it is? If you make $40,000 first year, 0 year, when you first initially get hired, and eventually end up making $90,000, what is the net change from 40 to 90? Obviously, it just makes good sense. It's $50,000, right? 90 minus 40, that's how much money you're making. But hold on a second. What if we had two people? We had one person that got hired in, and at year 0 is 40. And then we have another person that also, so we'll say that this is person A is the first set of numbers, and this is just me. I don't want you guys, this is me trying to conceptualize the questions we try to answer with calculus. And let's say this is another person underneath it at year 0. They start out making $40,000, right? And at, oops, sorry, I got big thumbs. Are you going to cooperate with me? There you go. He's cooperating with me. At $90,000 eventually as well, right? So it's the same situation, year 0, 40,000, year 0, 90,000. But guess what? Budget cuts start to happen within a company, and then they have to decide which one of these two people has to go. Well, how do they determine who's better? They both started off at the same place. They both ended at the same place. Well, guess what? That doesn't mean they're the same. Okay? And that's when we need to start talking about how long it took them to get there. If person A was a sharpshooter, and I mean what I mean by a sharpshooter was someone who's motivated, always trying to learn, not really having too many life issues. They get to $40,000 to $90,000 a year, let's say in 3 years. You can kind of tell that this person, and I'm going to be honest with you, the average raise in society right now is 6%. 6%. $40,000 to $90,000 in 3 years is unheard of, unless you're actually quitting a job and taking a job somewhere else. Okay, so over 3 years, you grew $50,000 a year. How much is that per year? Well, $50,000 divided by 3 years, that's roughly about $16,000 a year. That's a lot of money, but that's an indicator of this person's rate of change. How fast they are changing. Not just how much anymore, but how fast. Well, it's the same strike we try to go for with person B. Person B, let's say they got to $90,000, but before they got there, it took them 20 years to get there. $40,000 to $90,000 a year is very feasible. If it took you your entire career to get there, it just makes really good sense, right? But unfortunately, this person is unmotivated. That's what this says to me, unmotivated. So the difference is $50,000. $50,000 divided by 20 years. That's approximately $2,500, so $2,500 a year of a raise, which is nothing. be totally honest, is nothing. It's a little less than 6%. So what this lets you know is that person B is unmotivated. I'd be more inclined to fire person B. Now, what did I just talk you through? I just talked you through a giant concept, and this is what we're going to start talking about is the average rate of change. But not just average rate of change. This would be a concept from Math 1800 or pre-calculus. If you don't know what that is, I'll post the links in on here somewhere where you can actually go back and review what average rate of change is. We're going to need that in order to go through this, okay? This video might be a little longer than normal. I'm not trying to keep it to a half hour, maybe somewhere around 20 minutes, okay? So the average rate of change, okay? Average rate of change, or what we like to call the average rate of change is the secant, the slope of the secant line. And yes, these are going to sound like a lot of words, and then we're going to try to use the average rate of change to approximate what's happening at a particular place in time, which I will call the instantaneous rate of change. And that's actually called the slope of the tangent line. Okay, we will talk more about this and what they mean, but I figure we need a title before I scroll off the page. So here we go. So this is what we're trying to do. In this sector right here, we're talking about net change. Okay, oops, my handwriting has gotten worse over the years, guys. It's gotten much worse. Let me see here. I need to draw some stuff. Boom. Okay, so remember, so net change was the idea that someone made $50,000. Their output at the end of their career was 90K minus 40K. Well, that gave us a total net change of $50,000, right? Makes good sense. But good news is the time matters, okay? So at time equals 3, or the function of 3, right? And this was the function at 0. This is 3 years minus 0 years, right? This ends up becoming this, which is approximately $16.6 thousand a year. Okay, this idea, the numerator is the net change, but all of this, dividing it or averaging it over the amount of time, that's a different concept altogether. That's not net change. That is the average rate of change. Okay, so this is all calculus really wants to talk about, is not really the average rate of change, but this is the idea of just rates of change and stuff. Okay, so I have an example typed down here. I'm going to talk through, and this might end our video for the day, but it's going to be a great introduction to why we need certain things and how we go about doing it. Okay, so here's the idea. The weight W of a baby animal, right? I'm not going to specify which animal because I made this up. T months after it is born is given by W of t equals t squared plus 5 pounds, right? So that's the output. So every time you plug in a month, so at 1 month, this thing would be 6 pounds, right? At 3 months, this thing is going to be 3 squared is 9 plus 4, 14 pounds. That's a big thing. Now, here's the thing. It says, what is the average rate of change? I'll zoom in a little bit here for you to emphasize a little bit. What is the average rate of change that this said baby... Oops, I don't know what I did. What is the average rate of change that of this thing at? And I want to specify this at 3 months. Now in class, I realize that this is very, very easy to misconceive, because a lot of people tell me that, oh, the weight of this baby animal, it's pretty easy. All we have to do is calculate the average rate it's growing. Right, average rate, you know what, I can't spell today, so I'm going to abbreviate this as average rate of change over the interval, over some interval, okay, over an interval. And just so you guys are reminded, in general, the average rate of change over some interval starting at some point A to some point B is just this, given by some function. It'll be f of b minus f of a over b minus a. So going from A to B. So in this case, and these are our inputs, A to B, so in our function here, it's time, right? So if we were to use the average rate of change, we're trying to figure out at 3 months. Not over. Like the problem didn't say over the first 3 months. No, it wants to know at month 3, how much is this baby elephant or giraffe or narwhal changing. Okay, so let me give you an idea. I'm going to graph this thing for you, and I've taken the liberty of bringing up decimals. Okay, so here we go. There is t squared plus what is going on? T squared plus 5. Now, copy. What I want to do is I actually want to just display to you how this thing is going to take effect. Okay, so if we take a look at this graph, okay, they want to know how much it's changing. And once again, the average rate of change. So what does this look like to you? Well, for all you guys who are good at 1800, this looks a lot like slope. Y2 minus y1 over x2 minus x1. And why does it look like slope? Because it is slope over any 2 points. So for this particular graph, that's what I want to do. Okay, I just want to show you what this will look like. We're trying to figure out what's happening at month 3. So month 1, 2, 3, this is where it's at on the graph. We're trying to figure out what the rate of change is there, which is extremely weird. Why is it so weird? Because in order to find a slope, how many points do you need? You need 2 points. We always needed an x2, y2, x1, y1. But they want to know what the rate of change is right here. Touching a line. That's tangent. Tangent. So this line right here is called the tangent line. And his slope, the tangent line slope, that guy is known as the instantaneous rate of change, because we're looking at the rate of change at that one instant. And that is huge. That is not a small thing, because if I ask you how to calculate the slope at 1 point, you should be freaking out in your pants, because in the end of the day, we always needed 2 points. So what's the idea? Well, we kind of have a lot of issues with this, because slopes normally take 2 points. So what we did over time is we said, let me get rid of some of this. We still want the slope at that 1 point. But what they said to do instead is, okay, we can't get that slope at that 1 point, but let me get the slope over an interval. So let's say I wanted to figure out what the average rate of change was. Why? Because I want to know what the instantaneous rate of change is. That is the goal. I want to find the instantaneous rate of change. What's happening at that instant? So what I'm going to do is I'm going to try to average as much as possible, and hopefully I get there. So let me look at my first average rate of change. So I'm going to start at, let's say, this point. Whoops, I moved stuff. Sorry, guys. I'm going to start right here at this point. And then, if you look at the line that is drawn, we strike this line through. Can I get my toolbar? Boom. If you strike a line through here, I want you to pay attention to this one, because this could freak a lot of people out. That's the line I just drew, but check out the line we want. Oops. I want this line that's in black. So think about going from 0 to 3. Is this line going to be a good approximator of what slope that is? And if you're saying, yeah, you're out of your mind, being off a little bit means that you're off a lot. Just imagine if a mechanic was off a little bit. Your car for sure is going to break down, okay? We're all about accuracy now. So check this out. So what did I do? I went from 0 to 3. So if I look at the average rate of change on the interval from 0 to 3, then what does that leave us with? That leaves me with plugging in W of 3, because that's my function, minus W of 0 to figure out the net change, and then averaging that over the 3 months that's going to happen. Well, W of 3, I think, is 14. Let me see here. 3 squared is 9, plus 5 is 14. At 0, we get 0 squared is minus 5 over 3 itself, which gives me, what is that, 9? I can't add today. If it was 10, yeah, 9. It gives me a slope of 3, I think. If I'm looking at this correctly, which I do believe so. Guys, I'm sorry, but a slope of 3 is what we're saying. These two lines is a secant line, which cuts through 2 points. A secant line. So the average rate of change is the slope of the secant line, but that's not a good approximation of this line right here. So what do we do, the tangent line? Well, Newton was a very brilliant man. What did he say to do? He says, you know what, screw this point we start at. What if we try to get it closer? Instead, starting it at 2. Then that means we're looking at this point. Oh, that looks like a greater approximation. Because if we do that, oops, then our line could actually help us approximate the other line as much as possible. But note, it's still a little off. It's still a little off. So check it out. 2 to 3, the average rate of change, so this is round 2 of this, we get W of 3 minus W of 2. Oop, not 3 of 2, W of 2. W of 2 over 3 minus 2. Good news, denominator is 1. This is 14. You plug in 2, I think you get 5, maybe? Yeah, we get minus 9, and that gives us 5. Now, once again, that's 5. That's the rate of change, right? It's a slope, right? So if you take out the numerator, this is in pounds, this is in months, right? So this is pounds per month, okay? So that tells me this is 5 pounds per month. That's the rate at that secant line. But does that a good job of approximating the tangent line? So what should we probably do? Newton had the answer. He says, you know what? Let's just keep getting closer to 3 as possible. Because is 5 a good approximate? We have no stinking idea. So we're going to keep getting closer and closer and closer until we feel like we have a great enough estimate to estimate it. Okay, this is going to give me W of 3 minus W of 2. And all of these are average rates of change on different intervals, all for the main goal of approximating what the instantaneous rate of change is. Once again, I'm going to use a little bit more languaging here, just so you guys get a clear understanding of what I'm talking about. Average rate of change is the slope of the secant line, right? The instantaneous rate of change is the slope of the tangent line. Tangent means touch at 1 point. Secant means touch at 2 points, which is when we are drawing a secant line, it's always cutting through the 2 points, hence the average rate of change. So anyhow, back to my average rate of change, and this time I close up the interval even more. I said, you know what, let me forget all this. I'm going to make my point. I need black again. Sorry, guys, to be jumping back and forth with colors like this at 2.5. That means I don't want this point. Let's creep it a little closer. I want it right there. See how it's getting closer and closer to being on that line? Man, so as the interval gets smaller, the slope is actually getting pretty good at becoming up right on top of the other one. But notice it's not exactly that great to say it's exact. So what's this going to be? 14 minus 1125 is what my calculator says. And guys, I'm a big fan of using a calculator, but don't be to get through the medial calculations, but don't get dependent on it. If you can't do algebra, this class is not for you. This thing ends up being 5.5. I still think it's a little off. Let's creep it even closer. How close is the big question. I don't know. Close enough to I know for sure that's what it's going to be. Let's creep even closer. This is W of 3 minus W of 2.9. 3 minus 2.9. And I'm just going to speed right through this. Minus 13.41 over 0.1, which ends up giving me 5.9. All right, so now look at these values. This is what I want to bring your attention to. If you look at the average rate of change, going closer and closer to closer, they're using the average rate of change to approximate, again, the instantaneous rate of change. The first one over this interval is 3. We thought it was 3 at first. Then we chose a smaller interval to get closer to 3. Notice the numbers 0, 2, 2.5, 2.9. We're getting closer to 3. It's 5. 2.5, 5.5. You notice it seems like we're getting close to our value. 2.9 when we hit 3 gives us 5.9. It looks like it's probably going to be 6. So how do we confirm for sure? Well, I want to use some common sense here. If this is our number line, and this is where we're trying to get to, and we're talking about where we're approaching. We're approaching 3. We just did 0. We did 2. And then 2.5, and then 2.9, right? If this truly is going to be 6, then if we came from the same direction, it should tell us the same story. So just to confirm, I'm not going to plug in all the points on the right-hand side. Instead, what I'm going to do is I'm going to start at the interval 3, and I'm going to go 3.1 or 0.1. Now, what should that tell me? That should tell me I'm still going to get close to what I think is going to be 6. So this is going to be W of 3.01 minus W of 3 all over 3.01 minus 3. Whew, guys, this is a lot of verbiage, which is 0.01. And then finally, you do some math, and you get, what do you get here? What do you get? I did it. I promise you I did it. I don't feel like plugging it into a calculator. If you do it on the other side, you end up getting 9.0601 minus 9. And when you calculate all this down, it gets you 6.01 ounces per month. So I want you to take a look at this. So you tell me what conclusion we're supposed to draw. Okay? Bottom line is that on the left side, as we approach 3 from the left, right? The values, the average rates of change, got closer and closer and closer to what we think is going to be 6. We thought it was going to be 6 because as this one, the average rates of change is getting closer to 3, it's going to end up being 6. That's what we're thinking. Well, as it approaches it from the right-hand side, it looks like it's almost close to 6 on this side too. So I think a good approximation of the rate of change. And there's a couple different lines of verbiage. When I say rate of change at 3, it's the same thing as if they were to say the instantaneous rate of change at 3. 3 months, that's the units, is 6 ounces per month. Now, I don't know what you get. I don't know if you guys get the power of what we just did, but we just found the slope at one point without really having 2 points. And it seems like we did more work than this, but this is the purpose of calculus. This idea of approaching 6, right? That's going to bring us into our new concept of limits. Let me see how we're doing on time here. Okay, so we are running low on time as far as what we're trying to do, but guys, this is a huge piece of the puzzle, just being able to approximate the instantaneous rate of change by using the average rates of change, which is huge. Okay, and once again, just a quick review on verbiage. The slope of the average rate of change is called the slope of the secant line. It's called the secant line. Let me erase some of this again because it cuts through 2 points. A tangent line is a line that touches at 1 point. The instantaneous rate of change is the slope of the tangent line. The slope of the secant line is the average rate of change's slope. Okay, so with all this being said, guys, once again, in order to grow yourself, you got to do some things you've never done and put yourself into a place of discomfort. So keep pushing, and I'll see you on the next video. Adios.